Mechanics. Quantum definitions, quantum uncertainty relations. First, de Broglie relation, P equal to h cut k. Planck-Einstein equation, E equal to h cut square, h cut omega. Dispersion relation, that is the general dispersion relation, is delta A square equal to A minus average A whole square. General uncertainty relation, delta A square times delta B square equal to greater than equal to 1/4 of average of I of commutation AB average square. Momentum and position uncertainty, delta x delta p equal to greater than equal to h cut by 2. Similarly, energy and time and number of photons with wave phase. Dispersion relation in quantum physics corresponded to the variance in statistical mechanics. Wave function, probability, that is psi star psi square dx, probability density j equal to h cut by 2 mi by times psi star del psi del x minus psi del psi star del x. Continuity equation, delta rho by delta t plus divergence of j equal to 0. So j here is equal to this current density and rho is equal to psi star psi. Schrodinger equation, this is time dependent Schrodinger equation, h psi equal to e psi, e equal to I h cut del del t of psi. Particle at stationary states, that means the energy does not depend on time, so energy operator is simply the energy E. Operators, Hamilton conjugates, so A phi whole star psi dx equal to A phi star A psi. This is the Hermitian operator, conjugate operator. Position operator, x will give x also. Momentum operator, Pn equal to h cut minus I h cut del del x or h cut by I del del x. Here n times of that operator is simply to the power n. Kinetic energy operator minus h, so kinetic energy operator equal to p square by 2m. So we replace p there, so minus h cut square by 2m del 2 by del x2. Hamiltonian operator, that is kinetic energy plus potential energy. So kinetic energy we have this and potential energy is v only. Angular momentum operator, Lz equal to r cross p. So simply x py minus y px. And the angular momentum operator, L square equal to Lx square plus Ly square plus Lz square. Parity operator P operates on psi, that will change only psi r to psi minus r. Now expectation values, expression of A, it will be psi star A psi dx. Time dependence of that expectation value, the change of expectation value A equal to, so dA by dt, this is the expectation value, will be minus, will be delta by delta t of expectation value A plus I h cut of the expectation value h with respect to A. So eigenfunction A operate on psi, it will give some constant A n psi n, and the expression values of A will be this Cn square An. Ehrenfest equation, first equation will deal with the momentum. So expectation values of momentum will be m times of v, so delta average A, expectation of r and expectation change of expression or r with respect to time. Second term will contribute to force, so force delta t of momentum change. So expression of P equal to minus of grad of V. So expression of grad of V. These are the two formula theorem for Ehrenfest. Dirac notation AMN NM equal to just bra of N A ket M. Sorry, ket A N bra. So this is the bra notation and this is the ket notation, and scalar product simply psi star psi of psi n and psi m with over all x. Wave mechanics. So second term is wave dynamics. So potential, whenever the potential is step, so it has zero potential here, but after some distance it will have a step potential with potential V0. This is the definition. So wave number, I will do that. So h cut square by 2m del 2 psi del x2 plus v psi equal to e psi. So here for this, for region 1 we will make this v0. So in that case, so delta 2 psi delta x2 equal to 2m e. So we have this equation. So delta 2 delta x2 plus 2m e by h cut square psi equal to 0. This is k square. So k square equal to 2m e h cut square. So h cut square k square equal to 2m e. Similarly, to h cut square or q square equal to 2m e minus v0 by h cut square. So amplitude of reflection, that will be k minus q and k plus q. So it is less than 1. So amplitude of transmission coefficient 2k by k plus q. Probability current density J and J1 and J2, that can be written like this. So this probability current density J equal to h cut by 2mi psi delta x star minus psi star delta x. Earlier we have said, just we will use that formula to get this. Now potential OL, so it is 0 up to here, then again it goes to minus V0 and again it will go to 0. So in that case, whenever x within that A we will have 0 potential, and other part we have V0. Similarly, h cut square k square equal to 2m e and h cut square q square equal to 2m e plus v0. Now we can calculate the wave function for different region, and you can get the amplitude of reflection coefficient and transmission coefficients. The probability density also can be calculated in these two regions. And bound state, whenever the particle energy is greater than V0 but less than 0. So within that region we will have the bound state. So for even parity KQ A equal to K by Q, and odd parity minus Q by K. Barrier tunneling, so potential wall, barrier. So potential energy is 0, here V0 and here again 0. Similarly, h cut square k square 2m e, h cut square kappa square equal to 2m v0 by v0 minus e. The similar formalism, we can calculate this reflection and transmission coefficients. The tunneling probability also t square equal to 4k square kappa square divided by that whole term. So the tunneling probability will follow e to the power minus 4 pi kappa a times k square by k square plus k kappa square whole square times 16. Same way probability currents can be calculated. Particle in a rectangular box. So earlier we have 2L by sin n pi x by L or A. Now we have 4 such dimension x, y, z. So in that case 8 ABC and sin for different directions x, y and z. So energy levels are h cut square by 4m, L square by S square, M square by B square, N square by C square. Density of state rho E dE equal to 4 pi by h cube 2m cube e to the power half. So density of state is proportional to e to the power minus half, e to the power half. Harmonic oscillator, we have the kinetic energy plus potential energy half m omega square x square equal to E psi. Energy of the system n plus half h cut omega. The wave function can be described with the Hermite polynomial. And now hydrogen atom, quantization condition, angular momentum L equal to nh cut, Bohr radius a0 equal to 0.5 angstrom, orbit radius is Rn proportional to n square, total energy proportional to z square by n square, and fine structure constant is 1 by 137. Rydberg's formula 1 by lambda mn equal to r alpha, arithmetic mu by na z square, that is 1 by n square minus 1 by m square. Hydrogen like atom, similarly we can write hydrogen like atoms with a reduced mass formula, and this wave function contains all radial and the angular parts. Total energy, again we see that z square n square. Radial expansion expressions are r square 1 by r and r square average. So now allowed energy, let's say n equal to 1 2 3 like that. So L would be 0 to n minus 1 and m would be minus L to plus L. So psi equal to psi 1 0, the ground state, equal to e to the power minus r by a. First excited state equal to e to the power minus r by 2a times 2 minus r by a, like this. Orbital angular dependence, a is equal to 0, L equal to 0, s orbit when phi equal to y equal to constant, so we'll have a constant sphere of radius with a constant radius. With L equal to 1, we will have different values at px, py, pz. Based on that, these L orbits will form. Similarly, d orbit will have different configurations. Now angular momentum L equal to r cross p. Lz can be written h cut by I, x dy, y ddx, or h by I del def L. So L square will be Lx square plus Ly square plus Lz square. So ladder operator, L plus minus equal to Lx plus or minus I Ly. So whenever ladder operator operates on a spherical harmonics, it will give h cut L times L plus 1 minus m L times ml plus minus 1. So this is the orbital contribution, this is the magnetic quantum number contribution. Now L square will give L times L plus 1 h cut square, Lz will give ml h cut, and Lz operate on L plus L minus, it will give ml plus minus 1 h cut of L plus minus of y. So L have multiplicity of 2L plus 1. Angular momentum commutation relation. Angular momentum commutes z component of angular momentum commutes with the Hamiltonian, so it is 0. So Lz commutes with, so see, if x, y, z, it is like that, so in clockwise direction we will have a positive sign. So Lz x, so zx it will give y positive. LZY, so zy will give a negative minus x, and zz will give 0. Similarly with P also, LZ with Px will give a positive P of y. LZ with Py it will give minus of Px. Similarly Lx Ly will give Lz, so xy will give xz, zx will give ly, and yz will give ilx. L plus and Lz will give minus of L plus. L minus with Lz it will give plus of L minus, and L plus L minus will come into 2 h cut Lz, and L square with commutes with L plus and N minus. L square with Lx, Ly, Lz will be 0. Now Clebsch-Gordon coefficients. So let's say these coefficients make connections with product basis and the couple basis. So let's say we have two angular momentum, z1 equal to half and z2 equal to half. So we can have different m values for the system. So let's say half, this is j1, this series is j1, this is j2. So j1 have plus up or minus up based on this. So plus plus, plus minus, minus plus, minus minus. So these four configuration can be completed, can stay here. So these are the product basis. So these are the tensor representation of the angular momentum and the spins. So also now the couple basis, that is the representation of j and m. So j can have value from j minus 1 to j plus 1. So in that case, plus up minus plus up plus up, so maximum value is 1 and minimum value is 0. So for 0 we have m0, for 1 we have m value 0, minus 1 and plus 1. So these three, so total 4 values are there. So we will represent this couple basis in terms of this product basis with some coefficients, and these coefficients are called Clebsch-Gordon coefficient or CG coefficients. So we don't have to calculate every time what are the coefficient, rather we can search using these tables how this coefficient can be seen. So let's say, so Jm, this is the couple basis. Couple basis can be represented like this. This is the identity matrix or unitary matrix with Jm. So this term is the CG coefficient and this is the basis. So from this table we will try to calculate the CG coefficient. First J1, J2, identify the table. So this is the J1 or L1, L2. So J1, J2 we have to search first, then M1, M2, that will decide the row. So M1, M2, so for that particular M1, M2 we will search. And for what Jm is that J and M value is all the M values. So for that J we will go there. So where it will intersect, we will have that CG coefficient there, and we will make a square root of that value. Let's say we want to calculate CG coefficient for 3 by 2, 1 by 2 and 1 1, 5 by 2, 3 by 2. So here J1, J2 are 3 by 2 and 1 by 2. So we have to search 3 by 2 cross 1 by 2 table. See, this is the 3 by 2 cross 1 by 2 table. Now we have to find M1, M2. M1 is half and M2 is 1. So this is the M1, M2. So half and 1. So we will have to look this row. Now we have to find J and M. J and M is given by 5 by 2 and 3 by 2. So for that 5 by 2 is that and 3 by 2 is this. So this, where it will intersect, that is the value. So 3 by 5. So CG coefficient will be square root of 3 by 5. So in that way we can calculate, we can see the CG coefficient for couple and product bias. So also this product space to couple state we can express. So let's say we have 2 minus 2. So 2 minus 2, that basis we want to see. So in that case m1 m2 are 2 and minus 2. So this is the 2 and minus 2. Let's say we'll go 2 1 and 2 minus 1. So first j1 and j2 we have to find. 2 2, so this is the 2 cross 2, and m1 m2 is equal to minus this m1 m2, 1 and minus 1. Then we have to represent that with respect to this product basis, sorry, couple basis. So these are the couple state: 4 0, 3 0, 2 0, 1 0 and 0 0. So first term is 4 0, we'll have the coefficient of root over 8 by 35. Second will have 2 by root 5, root over of 2 by pi 5. Third term will have 1 by 14, square root of that, minus of 1 by 10. So minus will put outside, root over of 1 by 10, and last term will have minus 1 by root 5. So couple state in terms of product states. So let's say we wanted to represent 4 0, that is the 4 0 term, in terms of this couple basis. So that can be written. So first 2 and 2, that will be fixed, 2 and 2, that will be fixed. So these are the terms. So the next thing we have to add this 2 minus 2 here, 2 minus 2, 1 minus 1, 0 0, minus 1 minus 1, and the last term will be minus 2. So last term will be 2 minus 2, 2 plus 2, these states with the coefficient. Now we will add coefficient like 1 by root 70 here, root 70, 1 by plus square root of 8 by 35, square root of 18 by 35, and square root of 3 by 8 by 35, and this is 1 1. So square root of 8 by 35, and the last term will have square root of 1 by 70. Angular momentum addition, J will be the total angular momentum, L plus S, Jz equal to Lz plus Hz, and J square equal to L square S square plus 2L dot S. So Z multiplicity will be 2L plus 1 times 2S plus 1. Magnetic moments, these are the Landry factor, GL equal to 1 plus J times J plus 1 plus S times S plus 1 minus L times L plus 1 divided by 2 of that first term, 2 times of J times J plus 1. Quantum paramagnetism, that we don't need. Now perturbation theory, this is time independent perturbation theory. So in that case energy is a constant, like don't depend on time. So H operate on psi n will give En of psi n. So if the perturbed Hamiltonian is H0 plus H dash is the perturbation. So perturbed energy eigenvalue will be the with unperturbed value plus psi k expectation of H dash. So expectation of H dash will be psi k H dash psi k. The second order correction, this is the first order correction. Second order correction will be psi k H dash psi n average square divided by E of the first k, first term, first suffix, E of second suffix n, and it will be summed over all the terms. So when n not equal to k, this is the second order correction of energy. Perturbed eigenvalue, this is the unperturbed eigenvalue with addition to psi k. So we will have H dash, that will be operated with psi k, psi n, and ek. Again this suffix will come here, ek, minus this n will come here, en of psi of n. So here n not equal to k. The same thing here, it will come here without a square term and addition with a multiplication of psi n here. Time dependent perturbation theory. So in that case we will write the total Hamiltonian as a energy operator at the right hand side, and we will calculate the wave function psi t. So psi t will be Ct times psi n of e to the power energy dependence term here. So this Cn will be calculated using these following formulas. And Fermi-Golden rule, that is gamma I to F, that indicates transition probability per unit time from state I to F. So the transition probability of going one state to I to F state. There will be 2 pi by h cut psi f time get psi h dash bra of psi I square rho of E. High energy and nuclear physics, nuclear decay n times t equal to n0 e to the power minus lambda t. That n indicates the number of particles remain in the system. So at time 0 it will have n0 particle, but as time goes it will fall. Okay, so half time, whenever it reach half of the particles, then n times will be n by 2, n0 by 2, then t half will be ln 2 by lambda. So lambda is the decay constant and average of t is the mean time. So 1 by reciprocal of lambda is equal to mean time. Successive decay from 1 to 2 to 3. First one is same formula as this decay law. So n1 equal to n10 e to the power minus lambda t. But second one, the particle first, second, third, let's say A or first, second, third, first particle will decay to second, second will decay to third. So constantly this second will increase, again it will decrease. So third particle will constantly go up, but second will have it will come and again lose some particle. So n2 will be n20 e to the power minus lambda 2t. It will decay with that, but n0 will be produced n10 lambda 1 by lambda 2 minus lambda 1 times e of minus lambda 1 t minus e of lambda 2 times of t. For number 3 particle, it will not decay to anyone. So contribution from n0 plus contribution from n2 and contribution from n1. So n2 will be growing from 1 minus e to the power minus lambda t. Again n1 will grow like 1 plus lambda 1 e to the power minus lambda 2 t minus lambda 2 and e to the power minus lambda 1 divided by lambda 2 minus lambda 1. Geiger-Natter theorem. So log of lambda equal to b plus c cos r. So r is the range of the particle and b and c are the constant for the series of alpha, beta, gamma decay. Nuclear binding energy. From the liquid doped model, the binding energy is volume contribution, area contribution, the Coulomb contribution and asymmetric contribution. So and delta is the following for different z and n, both even, both odd, and otherwise it will be 0. So this volume contribution a to the power 1, for surface contribution a to the power 2 by 3, for Coulomb contribution z square by a to the power 1 by 3, for asymmetric term n minus z square by a. Semi empirical mass formula, number of proton times number of mass of the hydrogen atom, number of neutron times mass of neutron minus binding energy. That will be the mass of the system. So binding energy will be will reduce the effective mass. So that mass will change to the energy that will bind the system, bind the nuclei. Nuclear collision, we have Born scattering formula sigma by omega, equal to 2 mu by h car square integration from 0 to infinity sin kr by kr br r square dr. This is whole square. So this is the differential cross section. So relativistic wave mechanics, the Kg equation, the Kelvin Gordon equation, that can be written box square plus m square c square h car square psi equal to 0. Here box is d mu equal to 1 by c square d square dt to dt square minus nabla square. The Dirac equation also can be written like this time dependent derivative, like I h car del psi del t equal to minus I h c alpha dot nabla plus b m c square psi. This is the Dirac equation that can be represented with that expression also. So here alpha I square equal to 1, beta square equal to 1, and alpha I alpha j will have 2 delta ij I, alpha minus beta is 0, and alpha with alpha equal to 0 if alpha and beta I and j are not equal to, they are not equal. So with that one comment for this Kg equation, there are two problems that we have. So negative energy explanations cannot be given from that Kg equation, and second is probability density of the system is negative, so that is unphysical.